isomer. Okay, so I guess we stopped. So we learned how to draw, right, the chair conformer, and we discussed why the cyclohexane is special and why chair conformer is special, right? By having the chair conformer, you can be free from, right, the strain. Cyclic compound, most commonly found in nature, we discussed this as 6-member ring. This is a ring due to the fact that they could call the nearly strain-free chair conformer. So if you see the bond angle of the chair conformer, cyclohexane, it's close to the tetrahedral angle, right, 109. And all the adjacent bonds are essentially staggered. So if you are seeing, right, this chair conformer, maybe you can imagine your eye is here, right, and seeing this chair conformer and drawing the human projection. You can imagine this type of projection can be drawn. Right? It depends on how you are seeing, but basically you can draw the human projection, right? And from this human projection, you know that all the CH bonds, right, they are staggered. There is no eclipsing CH bond, right? And also the CC bonds, right? You can be free from the torsional strain, and also you know that you can be free from the angle, right, strain. So that's why the cyclohexanes, the chair conformer is unique. 그래서 뭐 사이클로헥세인 같은 경우에 왜 유니크한지는, 왜 공부를 많이 저희가 또 집중적으로 하는지 이유는 그때 설명을 드렸었죠. 스태그 컨포머를 가지게 됨으로써 이제 이클립싱 스트레인, 토션 스트레인으로부터 자유로워질 수 있고, 그리고 본드 앵글이 거의 109.5도가 되니까 앵글 스트레인으로부터 자유로워질 수 있고, 앵글 스트레인의 본질은 뭐였죠? 오비탈 오버랩이었죠, 그렇죠? sp3 하이브리다이즈 모델에 의하면 이제 테트라헤드럴 앵글을 가질 수 있을 때, 그렇죠? sp3 오버랩이 극대화될 수 있었죠. 사이클로프로페인, 그 비교가 머리에 기억이 남으실 겁니다, 그렇죠? 그래서 그냥 기계적으로 109.5도가 될 때 왜 좋은지 이유는 오비탈 오버랩이 극대화될 수 있기 때문에 sp3 하이브리다이제이션 모델에서, 그렇죠? 사이클로헥세인 컨포머의 경우에 이제 거의 109.5도에 근접한 번드 앵글을 가질 수 있기 때문에, 따라서 앵글 스트레인으로부터도 자유로울 수 있고, 앞에서 토션 스트레인으로부터도 자유로울 수 있고, 그래서 스트레인 프리 체어 컨포밍 스테이트를 가질 수 있기 때문에 사이클로헥세인 자연계에서도 많이 발견돼요. 그래서 중요하다. 그래서 공부하는 거다, 그렇죠? Okay, and we studied how to draw the chair conformers. So for those who are not familiar with, please practice a lot, and it is very important. Okay, so this is all the rules we discussed in the last lecture. So again, practice how to draw, and you need to know how to present axial and equatorial bonds at each carbon, right? And each carbon, we discussed this, right? There are up carbons and down carbons in this chair conformer. Right? You know that this is up carbon, up carbon, up carbon, and these are down carbons. Right? So you need to decide, right, the character of the carbon, up, down carbons, right? And also you should decide the side of the ring. Right? You can define the upside and downside. Right? So up carbons upside is an up extra bond. Right? Up carbons downside is an equatorial bond. And down carbons upside, right? For instance, this side, this is the equatorial bond, and down carbons downside is a down axial bond. Right? That's how you can define and discern the up and down side of the ring. Okay? So up carbons upside, it's an up axial bond. Down carbons downside, down axial bond. Right? Up carbons downside, equatorial. Down carbons upside, equatorial as well. Okay? So you can also, right, do back and forth, right? You can decide, right, whether this is upside or this is upside or downside, for instance, right? So this is the upside, down carbon's upside, right? And this side is the upside of the ring, right? Up carbon's upside, right? So these two are on the same side of the ring, for instance. So we'll learn in a few slides, in the next slide, I guess, to know how to define cis versus trans, right? Position, and you need to decide for that, right? Up or down side of the ring, okay? And we also discussed the ring flip, which is also important, right? The chair conformer, they can change their conformer state in ring flip. And these are all rules, right? Before and after the ring flip, the characteristic carbons get inverted. Up carbons change into down carbon. Down carbons goes into the up carbon. Right? And also the character of the bonds change, right? Get inverted as well. The equatorial bonds change into axial bonds and vice versa. Okay, all vice versa upon the ring flip. Okay, and how to draw it? If you know how to draw the one chair conformer, then you can imagine, right? Pull this carbon down, right, and push this carbon up. Right? By which you can make, right, this chair skeletal formula, and then you can apply all these rules, right? Inversion of carbon's character, inversion of bonding character, axial, equatorial, and vice versa. Down carbons, up carbons, and vice versa. Okay, that's how you can draw the different conformer ring state. And again, this the convergence called the ring flip. Okay. Applying this, you can perhaps draw this conformer and its ring flip version as well, right? So this is, right, up carbons, right? Equatorial, that means it's a downside. What about this metal? So this metal is on the down carbon, right? The down carbon's downside still. Okay, so I guess I mentioned in the last lecture, the side doesn't change upon ring flip. Downside is always downside. This metal is downside of the ring. Ring flip doesn't change, right? The side of the ring. Right? But in this case, right, the character of bonds change from equatorial to axial and axial to equatorial, vice versa. Okay? But again, this side doesn't change. But of course, the character of bond change from up to down, down to up. Okay? And we discussed why this component is more stable than the other. So we discussed the 1-degree dielectric interaction, right? Which is essentially the same thing with the gauge interaction or gauge destabilization we discussed the conformer of the butane. Right? Essentially the same thing, but there are two pairs of the gauge interaction. That's why the magnitude doubles. That's what we already studied, and you can do a little bit of math here. You can calculate and get the equilibrium constant and then plug in to the delta G equation, blah, 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 from which you can get the number, the ratio between the equatorial versus axial ratio. And we discussed, right, the number increase as the size of the substrate increase, right, which is quite intuitive, right? So you compare methyl versus t-butyl, for instance, right? The ratio which, right, equatorial occupy more, this is actually increased quite dramatically. Right? And then I guess we stop here. So now we can think about the disubstituted case. So we have two substituents here in this case, methyls. Right? You have methyl here and there, and we can define, right, cis versus trans. So for which you can think about getting the side of the ring, right? Side to which this substituent locates. So you can maybe define the side of this methyl with respect to the ring. So this is the up carbon's equatorial, right? That means the down. And this middle is the down axial, right, to the down carbon. So this is down, but they're of the same side. That's why this is cis. Okay. What about this? This is down carbon's upside, right? Equatorial. This is upside. This is same downside, right? But they are on the opposite side. That's why this is trans, right? They are not in a relationship of the conformer, right? So ring flip doesn't give you, right, the from left to right or right to left. This is not a conformer relationship. This is a geometric isomer, right? So cis-trans isomers, they are geometric isomer. They are not the conformational isomer. Okay? 그래서 앞에서 또 제가 몇 번 말씀드린 것처럼 링 플립이 일어난다고 substituent가 붙어있는 그 위치 사이드, 업사이드, 다운사이드가 바뀌지 않는다고 이야기했죠. 그렇죠? 그 컨포머 관계에 있다고 시스-트랜스 캐릭터가 바뀐다는 게 아니에요. 시스-트랜스 캐릭터는 컨포머리 컨버전에 의해서 바뀌는 게 아니에요. 그렇죠? 지오메트릭 아이소머에 분류되는 거고 아예 분류 체계가 다르다는 이야기. Okay? And you know how to define, right, cis and trans isomers. I guess so. I guess we stop here last time, and then we can continue. So you can decide, right, whether this cyclohexane, right, whether is this a cis or trans isomer. Then you can, of course, decide, right, decide to what each substituent is attached to. So this methyl is equatorial to the up, right, carbon. So this is down, right, and this is down. So this is down. This is cis. Okay. What about this one? You have down substituent. For this one, there's a down carbons equatorial. This should be up. They are the opposite side. Is a trans. Okay. So that's how we can distinguish cis versus trans. Okay. Then you can do the same thing across all these examples. You can, go ahead and practice.
수소까지 다 대표를 해줬죠. 완전히 보이실 겁니다. 업, 다운, 위치.
Right, so we can maybe check the answer. Right? So this chloride, right, substituent is attached to the equatorial side of the up carbon. So this must be down. But intuitively, you know this is a down because you have up hydrogen. Right? But this is down too. So this is the up carbon's equatorial. That means the downside. Right? They're on the same side, cis. What about B? You have up, cis. You have down, cis. You have up, down, trans. You have down, up, trans. Up, down, trans. Okay. So if hydrogen is given together, it is it is quite intuitive to decide down and upside. But if you don't have the hydrogen attached to you, and if you're not familiar with, then you can just apply the rule. Right? Down carbons, right? For instance, like materials, the up, right? And up carbons, materials are down. They are on this different side. The trends. What about the ring flip, right? And now you have to compare, right? So you can compare the energetics, which one is more stable for each case. So this is, you can double check whether this is cis or no, right? You have down, right? Which is cis. And if this you ring flip, then you can anticipate each or still keep the cis, right? This is just the ring flip, it's a confirmation of change. It's not the geometric isomer, right? So you can decide this is still down, this is still down, right? So it's the same side, cis. The ring flip doesn't change cis trans character. Okay, so this is a cis dimethyl cyclohexane. But you can compare the energetics, whether left side, the left conformism is stable or not, compared to the right side. This is symmetrical one, so you can anticipate these two are essentially same, right? But what happened with the trans dimethyl cyclohexane? You can double check first, right? Whether this is trans or no. So you have down, up, methyl. It's a trans. Okay. And these two are both equatorial, right? And you can imagine that after being flipped, both become axial, right? So does methyl go above the axial, right? This is an up carbon, this is down carbon. After ring flip, this carbon this is down, so down carbon goes up carbon, right? And its upside become up axial, right? What about this carbon? This carbon, right? This carbon is up on the left hand side. After ring flip, it's going to be down carbon, right? And it's downside, right? In the left hand side of the equatorial. But after inversion of the character, its downside become down axial. That's why you have both axial and methyl, okay? And since you know there are just 1 3 diaxial interactions for each pair, right? There's a hydrogen up, and you know that there's a Golgi type interaction, right? 2 pairs of Golgi type interaction, right? That will give you 7.2 kilojoule per mole. But you have one more, right, below, right? There's additional 1 3 diaxial interaction, so you have to multiply, right? 2. So in total, you will get 14.6 kilojoule per mole destabilization as compared to the left-hand side. Right? The left-hand side, there's no diaxial interactions because these 2 methyls are occupying the equatorial side. Right? So then you can anticipate, right? This one is much more favored. What about, in this case, you have 2 turbulal, right? Ladies, quite bulky species. Okay? And after ring flip, you can imagine that, right, these 2 will go down and make the actual position. And this methyl also going to the actual position because on the left hand side you have the equatorial methyl. After ring flip, this should go to the axial. And then you can imagine these 2 are not happy when, right, occupying axial positions. So this one is much more favored. Yeah. So the above case was a cis, right? And you can also practice by yourself whether this is cis or no. You know, this is a down, this is cis. Okay? Down, still cis. What about this? This is a trans. You have up, down. And after ring flip, you're still having up, down, methyl, and tubular, respectively. Okay? And then you can compare, right? Which one is more favored with this favor, right? So in this case, you have methyl, which will have the 1 3 diaxial interaction. Okay? So you have 1, 2, 3 axial hydrogen, and 1, 2, 3 axial hydrogen. So there is a 1, 3 diaxial interaction, right? The upside. What methyl? In this case, you have T-butyl, which is bigger than methyl, and there is a 1, 3 diaxial interaction, the downside of the ring, right? You have 2-butyl here, and 1, 2, 3, 1, 2, 3, okay? Diaxial interaction, 1 T-butyl, which is less stable in other words, right? So this is more stable. So you can decide which side is more stable, okay? So just compare before and after being flipped and decide which one will give you more stable energetics. Okay? So you can count and compare the diaxial interactions. Okay. So 연습을 좀 하셔야 됩니다. 근데 연습이 좀 되고 나면 이제 뭐 시스트랜스가 이렇게 존재할 때 링 플립 되면 어느 페어가 더 불안정 이런 것들이 더 직관적으로 보이실 텐데 직관적이지 않다. 연습을 많이 하시면 됩니다. Alright, so this is a related question, problem set, but I guess you can practice by yourself and you can check the answer next time, okay? But just applying the rule and principle we just discussed, okay? So you can decide which one is draw the more stable chair conformer of cis and trans, okay? So you can draw cis and trans conformer and do the ring flip and decide which one is more stable. You can compare, right? The magnitude and extent of the 1-3 diaxial interaction for both cases. And you can try to solve the problem too. This is more generalizable questions. So there are all the possibility you can think of, right? Cis 1-2, trans 1-2, cis 1-3, trans 1-3, cis 1-4, and trans 1-4. For each case, you can decide which conformer is stable, right? More stable than the other. Okay. Right, so chiral conformer was very special, right? You know, it's the free conforming state. But there's another conforming state that cyclohexane can accommodate. One example is the boat conformer. Looks like boat, right? You have flat pole type hydrogen, right? From this carbon, right? When this conforming state, right? The carbons, they can come to nearly tetrahedral angle, nearly 109 degree, which means still the both conforming state can be free from the angle strain. But if you can draw perhaps, right, the Newman projection of this both conformer, imagine your eyes again here and seeing from, right, the left, then we can perhaps identify this Newman projection. And from this, you can rationalize there exists a torsional strain or eclipsing strain. All the bonds basically, right, they're eclipsing to each other. So there's a torsional strain in this case. Okay. Ball and stick model also suggests there is a little bit of steric strain between this flag pole hydrogen as well, right? So combining this, right, from the steric strain from this flag pole strain hydrogen and also the eclipsing strain, right? Imagine both conformer will have higher energy compared to the chiral conformer, right? But again, both conformer can be free from the angle strain. There's twist version too, right? So both conformer, they can twist to accommodate this type of conforming state, right? By which you can decrease the steric strain. You can imagine, right, the distance between this flag pole hydrogen are now farther away compared to the normal bond conformer. So you can decrease the steric strain from them. Okay. Still, the bond angles from this both conformer is nearly 109. So you can still be free from the angle strain. You can save. There is a little bit of gain in terms of the steric strain. Okay. And this is the full energy diagram, right? Chair both and twist both, or twist both conformer, right? And you can compare the energetics, the chair conformer is the most stable, it's the almost strain-free state, right? And if you can imagine, right, following the green arrow, how you want the complement change the atom, right? Imagine this this carbon goes up to become half chair complement, right? This is called half chair, right? And then there's a twisting in bonds to be a twist boat, and a little bit of twist, and it will give you, right, the boat complement. Right? Boat complement again still have torsional and stirred strain, and the stirred strain comes from, right, the flexible resonance, as I mentioned, right? And then we can do a little bit of twist, the twist boat again, which is, by the way, a little bit more stable than just boat complement, as I mentioned, right? The twist boat complement, right? They can decrease the steric strain, so this part, right, can be reduced. That's why the twist boat complement is slightly less energy compared to the boat complement. Okay, and after this is just symmetrical, right? After twist boat, half chair, and become the chair complement, right? Okay, and from this energetics, right, the barrier is known, right, around 12.1 kilocalorie per mole. For this much energy, the kinetic barrier, we can calculate the number of frequency, how frequently the ring flip can take place. 10 to 5, right? 100,000 times a ring flip can take place per second at room temperature, right? And if you think about the energetics again, you can calculate the ratio, and the number is telling you, right, less than 0.1% exists as a different complement other than chair complement. So these are basically the major converters you can imagine, right, at room temperature. Okay, these can exist, but less than 0.1%. All right, that was about the chair complements, right? And there's special occasions when rings can fused, right? So fused rings defined as a case sharing two adjacent carbons. So you can imagine, right? This type of fused ring, right? Two adjacent carbon, they are shared by left and right ring, right? That's why we are calling this as a fused ring. If you think about, right, the location, right, relative location. So if you want to characterize this and this, right, pink highlighted one from the perspective of right hand side ring, right, then you can identify this as equatorial and equatorial side, right? And then you can decide, right, the character up or down side, right? This is a down, this is up. That's why this is called transfused ring. Okay? This is down, this is up. And then you can imagine there's another kind can exist, right? Which is on the right hand side, right? So you can still identify, right? This pink and this pink, right? Part, and identify the side. What the perspective of the right hand side ring, right? This is the equatorial, this is axial, right? And then you can decide the side. So this is the down, this is down. If you are on the same side, so this is this huge ring. What about the energetics, right? This is less stable, meaning higher in energy. Why that is the case? You can imagine there's a hydrogen, this is here and there, right? And they can have the steric repulsion, and that will increase energetics, right? Because we have some 1,3 diaxial type. I guess we don't have that figure. Okay, so you can imagine, right? This is the substituent, right? and 1, 2, 3, there's a hydrogen, right? And 1, 2, 3, there's a hydrogen, right? So these and these, they can have the 1, 3 diagonal interaction, right? And also there is another pair, right? This one can have 1, 2, 3, right? And yeah, 1, 2, 3, and yeah, I guess this can have the 1, 3 diagonal interaction with this hydrogen, right? And this can erase. Yeah, so you can imagine this is an axial substituent, okay? And this axial substituent can have 1, 2, 3, and 1, 2, 3 diaxial interaction, right? That's the origin why cis-fused ring have higher energy, in other words, less stable, right? Status. I guess this one is too far, right? Too far to have one. Maybe this one. Yeah, this one is quite far, so it's hard to define as a diaxial interaction. So you can imagine this one axial, right? From the perspective of this ring, can have the 1, 3 diaxial interaction, and that's why, right? Cis-fused ring has a higher energy. Okay. Right, and then you can also think about the ring flip, right, from the fused link system. So please think about this and practice how to draw the ring flip version from the fused rings. Okay. And this is how you can think about, right, one ring and the corresponding substituent can be considered, right? Considered as a pair of the substituent. So this one as a considered as a substituent, this one considering as a substituent. Okay, that's how we can define trans versus cis, or material versus axial. Okay, so 뭐. 조금 응용 버전이라고 생각하시면 되는데 한 링이 두 개가 같이 붙어 있잖아요, 그죠? 그러면은 붙어 있는 한쪽을 substituent 취급을 하면, 그죠? equatorial bond인지 axial bond인지 identify 할 수 있고, 그것으로부터 trans냐, cis-fused ring이냐 정의할 수 있고요. energetics 비교도 1, 3 diaxial interaction을 적용하시면 똑같이 substituent 취급을 할 수 있으면 이제 똑같이 axial substituent으로 취급을 할 수 있을 경우에 1, 3 diaxial interaction을 정의하실 수 있겠죠. 그러한 이유로 cis-fused ring이 더 불안정하다, trans-fused ring보다. 그렇게 이해하시면 되겠습니다. Okay. I guess that's it for component, and I guess we can move on to the isomer, okay, for the remaining time. I guess we still have 30 minutes. All right, so this is lecture, so we are lecture 9, okay? And we're moving, we're getting into the new chapter, okay? Chapter 4, so we finished the introductory part of the organic compound. So thus far we finished from chapter 1 through 3, and now we're entering chapter 4, and we're going to study isomer. So we'll discuss different type of isomer in this chapter, and most importantly we'll learn about, right, the stereoisomer, and geometry isomer is also important, but this chapter will cover up basically all the isomers you can think of. Okay. So what is the isomer? Isomer can be defined as a compound of different structure, but having the same molecular formula. Okay? And there are two major classes of the isomer. First one, this is what we are going to study, the constitutional, or in other words, the structural isomers. Okay? So that's the one type. The other type is the stereoisomer. Okay? So what is the constitutional or structural isomers? These are the isomers having different connectivity, or connectivity in bonds. So they do have different IUPAC names, okay? and they do have different physical and chemical properties. Okay? What about stereoisomers? They have same connectivities, right? But have different orientation in space. Okay? So they will have the identical IUPAC names mostly, but except for the prefix like cis or trans or R versus S, which we'll study perhaps next lecture. Okay? So these are the difference, right? I'm pretty sure you guys all know about this. So again, structural or conjugate isomers, they have different connectivities. Stereoisomers, they have different spatial arrangements of atoms or some groups. And this is the chart we can refer to. So isomer, under the name of isomer, you have conjugate isomer or structural isomers, and also the stereoisomers. Okay? Conjugate isomers, they do have different connectivities. Stereoisomers, they have same connectivities, but having different spatial arrangement. And under the stereoisomers, you can define, you can make a distinction between conformational isomer, right, and the configurational isomer. We just studied, right, conformational isomer, by the way, right? They cannot be separated. You cannot separate, right, one chair complement from the ring flip, the other complement, right? But configurational isomer, they can be separated, right? You can separate cis versus trans isomer, for instance, and also you can separate the R and S isomers as well. We'll discuss about that in the next class, perhaps. Okay, so under the name of the conformation isomers, there are two different classes in this chart, actually, but you can essentially think about the rotation about CC bond, the single bonds, or ring flip of the chair conformer. They all belong to this, right, conformation isomers. And then there's one special case, the amine inversion as well, right? They all still the conformation isomer. You cannot separate, right, two different conformer isomers. Okay. Under the name of configuration isomer, you have cis trans isomers and also the isomers that contain the asymmetric centers. Okay. So we'll study about this in details of that in the next class section. Again, constitution isomers, they do have different names, they do have different connectivities, a totally different compound, essentially, right? So they do have different physical and chemical properties. This example, ethanol and ether, dimethyl ether, they are in constitutional isomer relationship. All these examples, they are all the constitutional isomers. They do have still though, right, same molecular formula. If you count the number of hydrogen, carbon, and oxygen, they're all the same. But they do have totally different connectivities. They are totally different compound. Okay? So they do have totally different names. This is quite weird cartoons, but may give you some sense, right? Sense about conformation versus configurations. Right? This is gross, but they do have same IUPAC names, right? But again, prefix, of course, are different. You need to distinguish C versus trans, R versus S, right? So this can be explained to you, right? What is the different conformation? The same dog, you have, right? Same legs, right? And tail, but their postural positions are different, right? So you can have stable conformer, unstable conformer, right? But compound with different configuration, they do have, right, have different location, right? Tail and leg, they are different, right? So you can think about this as the difference, right? Difference between conformer versus configurational isomer, okay? So they can be separated, right? These two, you cannot separate. This is a one dot, basically, right? Only the conforming states are different, okay? And inside of the conformational isomer, again, we discussed, right, the conformation of the arcane, right? And also cyclic version. We discussed a lot about cyclohexane and its conforming state and its in the conversion, right, the ring flip. Okay? And this is the case for the amine inversion, right? So amine can invert it via this mechanism, right? So you can basically think about the umbrella, and umbrella can get inverted, right? And exactly how amine in this particular case get inverted to have different conforming state or conformation. So this is one conforming state, right? And this is the inverted conforming state. But their configuration is identical, right? But the only the conforming states are different. Okay. And inside the configurational isomers, you already know, right? Cis versus trans, and you know how to distinguish cis versus trans. Right? You have this up substitute, right? It's the same side of the ring, it's cis. You have up down trans, up cis, up down trans, right? This is the cis trans isomers. And the reason why they can be separated and they are different in configuration is basically the cyclic structures in most cases they restrict the bond, the rotation of the bond, right? There is no rotation, right? That's the critical difference between arcane or cyclohexane, which can do the rotation and ring flip. So basically result from the restricted rotation, right? You can have distinct configuration state, distinct cis trans isomers. So this restricted rotation, by the way, arises because of the cyclic structure, like this, right? Cyclobutane or cyclohexane, or right, double bonds or multiple bonds, right? Containing species, especially double bond, right? Containing species, they cannot rotate, right? You cannot break the bond, right? The pi bond, for instance, to make the rotation of the sigma bond. Right? So we'll discuss about that. So this is another example of cis versus trans isomers. You know, really this is cis. Right? You have these two are on the same side, these two are on the other side. Right? These two are the typical example of the cis versus trans isomer, which belong to the configuration isomer. Okay? Again, these are all the stereo isomers. Okay? Yeah, this is why, right, double bond can have distinct configuration, cis versus trans. So you know, right, from the hybridization model, you can rationalize the character of the double bond. There's one, right, sigma bond between, right, two carbon, and it's sp3 hybridized orbitals, and there's, sp2 hybridized orbital, right? These two are this bond, right, responsible and arise from sp2, right, sigma interaction. And there's one remnant, right, p orbital, which can have the pi bond, right? And in order to make, right, the rotation with respect to this bond, you need to claim, right, this pi bond is broken. Right? But the room temperature is not sufficient to break, right, this pi bond. That's why you need to invoke and claim two different configurations of state. These, right, substituents and these substituents will give you a different configuration of state. Right? So they do exist in two distinct forms, right? They do have different configurations. They differ the way the atoms are oriented in space. Okay. The ring type structure and double bond containing species, they do have, right, different configuration and different configurational isomer, right? And they do exist as a distinct form, and also have different, right, physical properties, and that's why you can separate. You can separate two different configurational isomers. Cis versus trans, for instance, they do have different boiling point, different dipole moments, right? Different boiling points here as well. So you can do, for instance, this tilt, right? To separate these two. There's a physical method you can use to separate, right, one from the other. Okay? And you know why dipole moments are different, cis versus trans in this case. What about this case? If you have, right, the substance on the same side of the carbon, right, and this carbon, for instance, have same linkage, right, hydrogen in this case, then for this structure, right, cis trans isomers are not possible, basically, right? because the two substituents in sp2 carbon, right, are basically the same, right? It's essentially the same. So you can imagine them, right, after the rotation, right? You can get the superimposed, right? You can maybe imagine, right, flipping out the structure and they will superimpose basically the same thing, right? So these structure, like having same substituent here and there, they cannot accommodate the different configuration of states and transisors. 그렇죠? cis 트랜스아이소머가 더블 본드를 중심으로 생길 수 있는 조건이 명시되어 있는 거죠, 그렇죠? 같은 서브스튜언트가 한 카본에 달려 있으면 링이 아니죠, 더블 본드 이 분자를 플리핑 시킨다고 하면 돌려보면 이제 슈퍼임포즈 되니까 같을 수밖에 없죠, 그렇죠? And there's a way, there's a rule to decide cis versus trans. This is a so now this is a complicated case, right? You have these three substituents, so you need to decide, right? You need to have a system to decide, right? Whether it's cis versus trans. So you have to declare the priority, right? Priority of substituent respect to the carbon, right? Carbon constituting the double bond, right? So you can decide, right, low versus high priority respect to the one carbon, right? And if you have such a system, right, that discern the priority, then let's say you can discern this is high priorities from each, then you can call out this is a G isomer, right? G means, right, same side of the double bond, right? And in German, this means together. I cannot call out in German, but you can just think about G means in German together in this case. And if you have such a system, right, and discern the priority of the substituent and giving this type, then you can call out this is an E isomer. E in German meaning opposite. Right? Then if you know the priority system, then you can decide, right, whether this given olefin is E versus G isomers. Okay? So you need to know the EG system of the nomenclature and EG system for the priorities as well. Okay? And this CIP sequence rules does for defining priority. This is quite general sequential rules. So you can think about the number of the atomic numbers. So higher atomic numbers, this should be up to the first point of difference, right? So you can decide, right, gain respect to each carbon constituting the double bond. You have to decide, right, whether this chloro group is higher priority or methyl is the higher priorities. Think about the atomic numbers. This should have the higher priorities. This is obvious case. Bromine group has to have a higher priority than hydrogen. But they are the same side, so G isomer. Okay. This case you have different side, E isomer. What about the bottom case, right? It's slightly more complicated, right? But you can apply this rule. Higher atomic numbers up to the first point of difference, right? You should go further, right? So again, you can think about from each carbon and decide, right, the priority. So in this case, you have carbon here. In this case, carbon here, same, right? So you need to go the next level, the next substituent, the next bond, right? So from the perspective of this carbon, you have one carbon, right, and hydrogen. Right? From the perspective of this carbon, you have the oxygen here, right? So you can decide this one is a higher in priorities. And you can do the same thing for the left hand side, right? You have same carbon, so you need to think about the next level, right? And this carbon has carbon and hydrogen, right? But this carbon has a bond with the chloro group, right? So you have chloro. That's why this is the higher priorities. But they are on the same side, G isomer. Okay? You can apply the same rule, same thing, but right hand side, identify this as an E isomer. Okay? What about the multiple atoms or multiple bonds, right? CIP rules apply for the priorities in this case, right? You can perhaps take an example. In this case, right, looks complicated, but if you apply the rule by logic, you can decide which one has a higher priorities. Right? So again, you need to decide from one side, right, from this carbon. This is a double bond moieties, right? In this case, you can count, right? There are two single bond with carbon. Right? There's a hydrogen and two carbon connection with two carbons, right? You can perhaps treat it like this, right? There's carbon, and H. What about this one? You have, from the perspective of this carbon, you have one carbon, but these two have two hydrogen. Okay? So in this case, this wins, right? Because you have two carbons compared to one right below. So this is the higher priorities. Can do the same thing for this case, right? You have to think about carefully though in this case. So from the perspective of this carbon, you have two hydrogens and one carbon, right? So from this you have CHH. And also from the perspective of this carbon, same, right? You have two hydrogen, right, and one carbon. So CHH, still same, right? So you have to move on to the next level, and you have to think about from the perspective of this carbon, okay? In this case, from the perspective of this carbon. Okay? On the upside, you have the bond with oxygen, right, and two hydrogen. Okay? What about this carbon? You have triple bond, right? But the carbon next to it, so you can treat it. There are three connection with carbon, CCC, and then oxygen wins. So you know this is higher product. Okay? That's why it's G isomers. What about this case? You have isomers and D wins hydrogen. Okay, so D wins hydrogen. And we can apply the same thing. You have, in this case, carbon, and this carbon has bond with two carbons and one hydrogen, CH. This carbon also have two connection with carbon, right, with CH. So you have to move on to the next carbon, this carbon versus this carbon. This carbon has three hydrogen, HHH. But this carbon, right, has a bond with the carbon, right? It's a double bond, so you have to treat it. This still has, right, one C and HH. Okay, that's why the bottom one wins. So they are on the same side, G isomer. Okay. Which of the following structures is E isomer? And you can decide. We can check the answer next lectures, but try to solve one, applying the rule that we just did. Right? You have to think about the priority, decide which one has a higher priority with respect to the carbon constituting a double bond. 네. 한번 연습을 해보시기 바랍니다. 답은 다음 시간에 맞춰볼게요. Right, so that was the cis-trans isomers, and then we'll move on to the different type of the stereoisomer, the isomer that contain the asymmetric center. So we'll define the asymmetric center in the next slide. So you've probably heard about chiral versus achiral molecules, right? And you can imagine, right, if you have a given objective, you can think about the mirror image of that, right? Do that for every object in the world. Okay? But there is a difference, right? Mirror image sometime, right, may or may not be superimposable. It depends on the character of the object, right? And we'll apply this to the molecule as well. Some molecules like hands, right? You think about hands, right? Your hands, left and right hands are mirror image, right? But they are not identical or superimposable, right? So you have left hand side here, the left hand, and its mirror image, right? The right hand, but they don't, right? They are not superimposable, right? They are non-superimposable. Right? And you can think about the structure of the molecule and apply the same thing, right? You can draw the mirror image of that, right? A given molecule, and decide whether they are superimposable or not, right? So molecule or object that is not superimposable on its mirror image is defined as chiral, or said to be chiral. Okay? That's how you can define in the first place chiral versus achiral molecules, or generally speaking, this can apply to any object in the world. But since we are studying chemistry here, the organic chemistry, we're thinking about the organic molecules. Same thing, but you can think about the other object too, like two socks given here. Two socks from a pair are mirror image, and they are superimposable in this case, right? So they are achiral in this case. And chiral means hand in Greek. Okay? So we can say right-handed, left-handed molecule sometimes. This is the expression sometimes you can use when you will encounter the textbook. Okay? Right-handed molecule, left-handed molecule. So applying the definition, right? Chiral versus achirality, right? Superimposability against the mirror image. Every object can have mirror image, right? The thing is whether they are superimposable or not. 그래서 이게 chiral, achiral을 이제 결정짓는 대정의입니다. 그 대정의 아래 이제 뭐 여러분들이 항상 모든 분자의 미러 이미지를 가까이 그려놓고 돌려보면서 이게 슈퍼임포즈를 하냐 안 하냐 뭐 해보실 수도 있죠. 근데 약간 성가실 수도 있어요. 분자 구조에 따라서. 그렇기 때문에 저희가 이제 이 chiral, achirality를 정의하는 그런 구조적 요소가 무엇인지를 파악을 해서 그걸 일반적으로 적용하시게 되면 이제 그냥 직관적으로 바로 이 분자는 chiral하다, achiral하다를 구별하실 수 있게 되는 거고, 그거의 중요한 기준 중에 하나가 뒤에서 다루겠지만 asymmetric center라는 개념입니다. 분자 구조 이렇게 물분자 같이 간단한 분자는 미러 이미지 그려보고 슈퍼임포즈 되는지 안 되는지 쉽게 알 수 있죠. 슈퍼임포즈 되잖아요. 그렇죠? 밑에 이 같은 분자도 되고. 그렇죠? 근데 이거를 분자 구조가 조금만 복잡해지면 미러 이미지를 그려보고 슈퍼임포즈 되냐 안 되냐 그냥 따지기가 대전제만으로 구별을 하기가 쉽지가 않다. 그렇죠? 그래서 저희가 부수되는 어떤 특질을 배우는 건 그것만 알면 적용하면 chiral 하냐 achiral 하냐 알 수 있고 그 완전히 asymmetric center가 등장하는 거예요. Okay, so applying the general definition of chiral versus achiral, right, molecule, we can check chirality check for the water. The simple molecule can do that. You can imagine the image, the mirror image of a given molecule here, water, and they are of course superimposed. So they are not chiral, they are achiral molecule. What about this? You have CH bonds, and they are chloro, bromo, and chloro moieties. Right? And of course, you can draw the mirror image of that. You can imagine there's a mirror in the middle, and draw the mirror image of that. And then you can decide whether this is superimposed each other or not. You can rotate the structure, and you rationalize they are superimposed, right? Which means this is still the achiral, right? Or non-chiral molecule. And there's a special character for the achiral molecule. They usually have, right? Usually have a plane of symmetry. So for the previous case, you can imagine there's a plane of symmetry inside of the structure of the molecule, right? If that is the case, then the molecule, in most cases, is achiral. There's the exception to that. We'll discuss that probably next class. But this is usually achiral molecule containing plane of symmetry, right? So if you think about the geometry molecule, and if you can define the plane of symmetry inside, right, then probably the molecule is achiral. What about more complicated case, right? If you have more complex molecule, then drawing for each their mirror image and check whether it's superimposed or no is not practical, right? That's why we need to define here the concept of the asymmetric center. So asymmetric center is defined as a carbon, for instance, in this case. They do have 4 different moieties, right? 4 different substitutes. In this case, you can start this carbon and define as an asymmetric center, right? Or sometimes it's called chiral center, which is again defined as an atom bonded to 4 different groups. And if that is the case, then in all cases, right, in this type of like bonding and structure and configuration, you draw the mirror image to that, and they never superimpose, right? Another terminology here, carbon atom with 4 different group is called tetrahedral heterogenic center. We'll distinguish the asymmetric versus heterogenic center in the next lecture. But for now, we can think about essentially same thing, but they are not exactly the same. Take an example here for octanol, right? You can identify, right, 4 different substituents with respect to the central carbon. That's why you have star here, meaning this carbon is asymmetric center. Okay. What about this? You have methyl, hydrogen, ethyl, bromo, 4 different groups. So this central carbon is asymmetric center. Okay. This one, same. You have 4 different substituents. This carbon can be defined as a asymmetric center as well. So you can locate the asymmetric center, which is quite easy. Examine each tetrahedral carbon atom in molecule and look at the 4 groups. If they are all different, right, then it's an asymmetric center. Okay. And then always omit from the concentration all carbon atoms that cannot be tetrahedral heterogenic center. These include these moieties at CH2 and CH3 groups, right? They do have, right, 2 hydrogen and 3 hydrogen. They cannot be asymmetric center, right? Any sp or sp2 hybridized carbon, it cannot be an asymmetric center as well. This is an example which we already covered, but we'll discuss, right, heterogenic versus asymmetric center in the next lecture. More of asymmetric centers, you can identify perhaps why this carbon is asymmetric center here and there, here, right? You can decide, right, whether the 4 substitutes in respect to this indicated carbons are different or not. So how many asymmetric carbon centers are found in this complicated molecule? Which is a drug, by the way, used to treat the Parkinson's disease. Okay? So you can check each carbon, right, and check substance are different or not. Okay, you can check the answer. Here's the answer actually. So please check this answer in practice. This carbon, right, has 2 different substitutes. This and this are different, right? And there's a hydrogen, and this also different moieties. So 4 different moieties. That's why this is asymmetric center. This carbons too. You have hydrogen here and there, by the way. And with respect to this 2 carbons, right, other 3 substituents are all different, right? Obviously different from hydrogen, right? That's why these 2 are asymmetric centers as well. 3 is the correct answer. And you can check the other carbon, right? CH2, CH2 moieties, they cannot be asymmetric centers we discussed. They already have single moieties, which is hydrogen. Okay? CH2, and this is double bond containing part. And this one, they have 2 identical hydrogen. They cannot be the asymmetric center. Okay? And you can double check the other spot if you want. Alright, so I guess we'll discuss this in the next class. So we can stop here and continue to discuss the stereochemistry. So we'll define again the asymmetric center, heterogenic center, and all the requirements. 네, 그래서 오늘 여기까지 하고